This is our third lecture covering the material in Chapter 12. And I'm going to break the rest of the material into two separate lectures so we can digest this chapter in a number of small pieces. In this video, we're going to cover the t-test. So we're going to do a hypothesis test. We're going to talk about some of the theory behind the hypothesis test, and we're going to apply the hypothesis test to the example that we've been working through together in the video lectures, the Reed Auto Sales example. And I'm also going to ask you to continue the set of questions that are associated with the checkpoints in this video when we get to the appropriate point in the lecture. So we're going to continue to assume that the Gauss-Markov conditions, or the assumptions that we covered at the end of the last video lecture, hold. So we're going to assume that we have all of the assumptions satisfied right through the assumption of a constant variance for the population error term, sigma squared. And that's the focus of this slide, is talking a little bit more about estimating sigma squared. So with all of those assumptions satisfied, we know that ordinary least squared is the best linear unbiased estimator, number one. Number two, we're also going to assume that either that error term is normally distributed, or we have a large enough sample so that the central limit theorem will allow us to establish that the sampling distributions of B0 and B1 are normal, so that we can conduct our hypothesis test using t-tables or z-tables if the sample is large enough. So in order to talk more in detail about the sampling distributions of B0 and B1, our sample estimates of beta naught and beta 1, we need an estimate of the variance of the population error term. And the estimate that we're going to use is what's called the mean square error. And the mean square error is based on the sum of square error, which we talked about in relation to regression analysis in the previous video lecture. It's really the sum of the squared residuals. So the residual in the regression analysis is the actual value that y takes on minus its fitted value. That's the residual, and we square it and we add it up across all the different observations, and that's what we call the sum of square error. This is the basis for estimating the mean square error, or our sample estimate of the variance of the population error term, epsilon. Remember, the epsilon was what we used as our symbol for the population error term. So what we're doing is we're really taking that sum of square error and we're averaging it for the mean square error. We're averaging it by dividing it, though, by n minus 2. That's our degrees of freedom in this case. When we had the sample mean, we divided by n minus 1 because we only estimated one parameter, the sample mean, from the sample data, so we lost 1 degree of freedom. Now we're estimating two things from our sample data, beta naught and beta 1. So we lose 2 degrees of freedom because we're estimating both parameters. So the appropriate degrees of freedom here is n minus 2. So we calculate the sum of squared errors exactly as we did in the last video, and we divide by n minus 2, and we get what we call the mean square error. That's our sample estimate of the variance of the population error term, epsilon. Now, we'll also want to take the square root of that sample estimate. That'll be an estimate of the standard deviation. And we call that standard deviation the standard error of the estimate in regression analysis. So if an econometrician is talking to you about their regression model and they state the standard error of the estimate, this is what they're talking about, square root of the mean square error. S, you'll see on the following slide, shows up in formulas that describe the sampling distribution of beta 1, or B1, the sampling distribution of B1, and it would show up in the sampling distribution of B0 too, but we're going to concentrate on hypothesis testing surrounding the slope. Okay, so here's the hypothesis test. This is a hypothesis test that is just a standard routine part of regression output. No matter what package you use to do a regression analysis, standard output would typically include the results of this hypothesis test. You don't even have to ask the software to produce it. The null hypothesis and alternative hypothesis are stated as a two-tailed test with this standard hypothesis test, where the null hypothesis is that beta 1 is equal to 0. In other words, the null hypothesis is that there's really no relationship between your x and y variable, that there's nothing to your model. That's your null hypothesis, nothing to your model. And your desired research result and what you'd like to show, that's your alternative hypothesis, of course. And that is that there is some important relationship between your x variable and your y variable. And so stated as a two-tailed test, that's an alternative hypothesis that beta 1 is not equal to 0. Okay. Now, sometimes you might be working with some economic theory that you're testing, which would give you more than just beta 1 not equal to 0. You know, it might give you beta 1 positive or beta 1 negative, in which case it might be more appropriate to do a one-tailed test. But the standard output is going to give you the results of a two-tailed test, and that's the only test that we're going to cover here. So with that null and alternative hypothesis, we of course need a test statistic. That test statistic is based on the sampling distribution of B1, our sample estimate of beta 1. Remember, beta 1 is a parameter. It's fixed. It's not a random variable. But B1 is a random variable, and it has a sampling distribution. And we're going to want to think about how to normalize that sampling distribution to come up with t-scores and do hypothesis tests. So the t statistic that's associated with this standard hypothesis test is calculated just by taking the value of the coefficient and dividing it by the standard error of the estimate of B1. Okay, so I mean implicitly there's a B1 minus 0, right, where 0 is the value of the test statistic under the null hypothesis. So it really does look a lot like the test statistics we've been working with before, but there's no sense in really kind of putting the minus 0 in there anyway. So it's just implicitly there, and that's the value of the t statistic. And so the question is you know, this t statistic measures beta 1, how far away it is from 0 in terms of standard deviations, right? That's what it measures. And the question is that value of beta 1 large enough relative to the standard error of beta 1? Right? Are we enough standard deviations away from 0 to conclude that we have a significant relationship between the x variable and the y variable, the dependent variable? And then here, this is just a formula, just to be complete. This is the formula that you use to calculate the standard error of beta 1 for that, you know, for the sampling distribution for beta 1. And it is based on S, right? The calculation that we did in the previous slide, the standard error of the estimate. Okay, so that's the standard error of the estimate. We would divide that by the square root of the sum of the squared deviations of x from its mean, and that's the standard deviation of the sampling distribution of beta 1. Now, you know, this is all pretty cumbersome to do by hand, but it, you know, like I said, most computer packages, they just routinely produce this output for you. You should still know how this stuff is calculated if you want to know how to interpret it correctly, which is why we're going over it carefully. We'll want to think about a rejection rule, and we'll reject the null hypothesis either if the p-value, which is also a standard part of regression output with most packages, if the p-value is less than the pre-chosen level of significance. Okay, just like before, this is no different from the other hypothesis tests we've done. We do have to remember, though, that it's a two-tailed test, but when computer packages calculate this p-value for you for the two-tailed test, it's going to give you the whole p-value. It's going to remember to take the area left over in the tail and double it to give you the p-value associated with the two-tailed test. You won't have to worry about that. And if you want to, you can look up in a table, you can look up the critical values. Okay, and then if you have a test statistic that's negative, compare it to the negative critical value. And if it's smaller, reject the null. Or if you have a positive test statistic, compare it to the positive critical value. And if it's greater, reject the null. Usually with regression results from a computer, this won't be the approach that you'll use because the computer will just spit out the p-value for you. And you can just look at the p-value and compare it to alpha and be done. So, I almost never use the critical value approach if I'm looking at computer output for regression analysis because the p-value is already provided for me. But we'll cover both, here just to be complete. Okay, so T alpha over 2, of course, is a T distribution, but this time I just want to remind you again that we've estimated both B0 and B1. So we've lost 2 degrees of freedom. So it's n minus 2 degrees of freedom is the appropriate degrees of freedom for the T distribution. Okay, so just step by step, our 5 steps. We've already determined the null and alternative hypothesis. We talked about that on the previous slide. But I just want to show you all the steps because I've been doing this 5-step procedure for you, all throughout the whole course. Step 2, determine the level of significance. Typical levels of significance for this two-tailed test would be 10%, 5%, and 1%. We're going to pick 5%. We'll take the middle road here. Of course, step 3 is always to go out and collect your data. This time we would be collecting data on 2 different variables, right? And then we would complete our ordinary least squares regression analysis. Now, I would recommend that before you jump in to doing ordinary least squares regression analysis, that you go back to module 1 of this course, right? And you do a complete descriptive analysis of your data, get to know your data, check for outliers, plot your data, do contingency tables, do all that kind of stuff, and really get to know your data before you jump into ordinary least squares. But assuming that you've done all of that work and you're ready to get going with your modeling process, complete your ordinary least squares regression analysis and calculate your t statistic. And again, I've already covered this. It's just B1 divided by the standard error or the standard deviation of the sampling distribution of B1, all covered on that previous slide. Again, this will routinely be produced for you in the computer output, as will the p-value associated with it, okay? So the rejection rule will be to reject the null hypothesis if the p-value that the computer reports is less than or equal to 5%, since we picked a 5% level of significance. And if you want to, you can use the critical value approach. I use Excel to look up the critical value for a two-tailed test at a 5% level of significance with 3 degrees of freedom, something I'm sure you know how to do now too, and I got a value of 3.182. So if you want to, you can compare the t statistic here that you calculated in step 4, right here, you can compare that to 3.182 to determine whether or not to reject the null hypothesis. It's up to you. I highly recommend using the p-value approach. So going back to our read auto sales example, okay, you could, if you did this on a computer, just like we kind of did it by hand before, the slope coefficient is equal to 5. Okay, and the standard deviation of the sampling distribution, which is based on the deviations of x from its mean across all the different sampling points, and it's also based on the standard error, the estimate S that we talked about back at the beginning of this lecture. If you put all that information together, you'll find that the standard deviation of the sampling distribution of B1 is equal to 1.08. So you take the ratio of the two and you get 4.63, and that's the value of your test statistic. Pretty big test statistic. So I'm guessing here, just based on my experience, that we're going to reject the null hypothesis and conclude that we found a statistically significant relationship between the number of ads that Read Auto runs on the weekend before a sale, and then the number of cars they sell the following week. So let's see. We're going to determine whether or not to reject the null. If t is equal to 4.63, you can, look up the area that's in the upper tail, and that'll be 0.01, and then you double it to get 0.02, and that's the p-value. If the computer reports a p-value for you, just routinely, it will be the 0.02. You won't have to double it. It'll give you the 0.02 value, okay? Then you would take that 0.02 value and you compare it to 0.05. And since it's smaller than 0.05, our rule says reject the null hypothesis, that we have not found a statistically significant relationship, in favor of the idea that, we have actually found a statistically relevant relationship between ads that are run and cars that are sold. It's that simple, okay? Also, we could take the 4.63 and compare it to the critical value that we looked up on the previous slide. Now, 4.63 is positive, so we want to compare it to the positive critical value of 3.182, not the negative critical value of minus 3.182. So since 4.63 is bigger than 3.182, of course, again, we reject the null hypothesis. I would like you to answer some more questions about our video lecture checkpoints, continuing with the beta analysis example.